We'll now take a look at ordered arrays or sorted arrays, where the elements in the array have to be organized or sorted in some order, whether it's increasing or decreasing. I want to start off by saying that we really don't consider sorted arrays to be a different data structure from an unsorted array. They're still arrays. But the reason why we want to mention some things about sorted arrays or ordered arrays is that the running times of some of the operations that we talked about are actually different if the array is sorted. So we want to take a look again at inserting, deleting, and searching and see how the running times of those operations would change if the contents of the array were sorted in some order. We'll start by discussing how we would handle inserting. So if we want to make sure that the array is still sorted, we can no longer say that we want to insert at the beginning or at the end, because if we decide I want to insert something at the end and then the order is not maintained, that's a problem. We have to ensure that the entire array is sorted in some order. So we can no longer just say insert at the beginning or end. So those are no longer options. Instead, we have to find the index where we want to insert the element. So it's not even saying that we want to insert at a specific spot. We have to say we want to insert this element, and then we're going to have to search through the array until we find the appropriate place to put this. Now we can't just use our typical sequential search to do that. So our normal searching algorithm isn't going to work because it's most likely the case that the element is not already in the array. So if we're trying to put something new in there and we use sequential search, it's just going to return a -1 and say it's not there. So what we have to do instead is we go through the array starting at the very beginning. And here we're going to assume that the array is sorted in increasing order from smallest to largest. So we keep looking at each element of the array until we find the first element that is greater than the element we want to find. That is where we would want to insert this new element, because then the order would be maintained. And then what we would have to do from that spot onward is we would have to open up a gap. So we would need to move the other elements of the array to make room for that one spot. So you can kind of think of it as once we find the index of where we want to insert it, then we can say insert at that specific spot. Here's the code that handles inserting an element in a sorted array. So we have to pass the array, the size, and the item that we want to insert. We still have to make sure we can make room in our array. So we still have to make sure that the size is less than the length of the array. Now this first part right here takes care of looking for exactly where we would want to insert this element. So we let I be the index of where we're going to insert. So we start at 0. And here I'm going to use a while loop instead of a for loop because we're actually doing some stuff with I. So I don't want to mess with using a for loop because you can do it with a for loop, but it gets a little bit messy. So in our while loop, we have two conditions. We make sure that I is still less than size, and we also make sure that AI is less than the item that we want to insert. Because what we're doing here is we're going to keep incrementing I until we either get to the end of the array, which means that the item we want to insert is the largest among all of the items currently in the array, or we keep going until AI is greater than or equal to the item, because that lets us know where we want to insert. So when this while loop is done, I is going to be the index of where we want to insert this item in our array. The for loop that comes afterwards you should recognize, because now we're just basically implementing the insert at some specific spot or insert at index code for inserting an element. So here J is going to be starting at the other end of the array, and we just simply keep making room for all those elements. So we keep making a gap and moving things over until we get to I. And at that point, we would put item into AI, and then finally we need to increase the value of size. Now, once we're done with this, we still need to figure out how much time this is going to take. So what we find here is that we're going to process each element of the array in some fashion. We're starting at the beginning and we're trying to search for the index that we want to add, or the index that we want to do our inserting. And then once we find it, the other elements are going to be moved. So we're processing every single element of the array. And what this means is that this whole thing is going to take O of n time. So what about deleting? Well, the good news is we can use the exact same methods that we used for unsorted arrays because we're not inserting anything in here. So if we take something out, it's not going to really have an impact on whether or not the array is sorted. It's still going to be sorted no matter what. We just have to keep closing the gaps, whether we delete at the end, delete at the beginning, or delete somewhere in between. So there really is no impact for deleting. Now, what we're seeing here is that for both inserting and deleting, it seems like sorted arrays are inefficient because both are going to take O of n time. So why would we use sorted arrays in the first place if adding and removing stuff is a little bit slower than what we've seen for unsorted arrays? The benefit that we're going to see is with searching. This is the reason why we would have an ordered or sorted array. So let me ask you, how would you search for an item in a sorted array? Take a minute to think about it. Pause the video if you need to, and then resume when you think you have an answer. The most likely response that you would think is we would start at the beginning if the item is small, or if the item is large, then we would start at the end of the array. So if the item is small, we start at the beginning and we just keep comparing elements until we find the item that we're looking for. Or if we know it's a large array, or a large value, we'll start at the end of the array and then work our way backwards. And on average, this should cut down the number of searches by half. That's pretty good if we can cut down the sequential search in half by just choosing where we start. But the problem is this approach is still going to take O of n time. It's still going to take linear time just because based on how the elements are set up, you may still be searching most of the contents of the array. So what we're going to see in the next class is we can do something even better, which is what we call binary search.